And we will move on now from the topic of post-quantum cryptography to actual quantum cryptography in our next talk. The next talk is held by Kevin Füchsel. He holds a PhD in physics. He has spent more than 7 years as a senior director at the Fraunhofer IOF. And last year, in 2020, he was one of the founding members of Quantum Optics Jena, of which he is also the CEO. Hello, welcome Kevin to our Quantum Summit at Stage Bob. In this section particularly, as you have probably figured out, very well named with our stage names. I'm looking forward to your talk. I'm excited to hear your explanations and descriptions of quantum cryptography, and the stage is yours.
Many thanks, Roman, and welcome to our talk. I hope you can see my slides. Just give me a short okay.
Yep, we can see it.
Yeah, right. So welcome to my talk based on entangled photons for quantum-based cybersecurity. So in the next minutes, I like to show you what's possible with quantum technologies. First, I like to introduce the company, Quantum Optics Jena. So we are a startup or a spin-off from the Fraunhofer Institute of Applied Optics and Precision Engineering, IOF, which is also located in Jena. So Fraunhofer IOF is very known for photon sources or laser sources. As you can see on the right, we have a history in entangled photon source. So last year, Chancellor Merkel, the space-proofed entangled photon source of the IOF was one of the exhibited at the Digital Summit in Berlin. So we found Quantum Optics Jena just a couple of months ago. So the CTO of the company is Oliver de Vries. My name, Kevin, as mentioned by Roman. And we get our first seed funding from the BMT, which is a local venture capital giver, ELAS Technologies, and the Fraunhofer Tech Transfer Fund, which is located in Jena, in Munich. And of course, we have a credible team of photonic enthusiasts and cybersecurity experts. And as a short side note, we are hiring. So if you feel comfortable with photonics or cybersecurity, feel free to give us a call or write us an email. So what's our mission at Quantum Optics Jena? So we believe that quantum technologies can or enable us to achieve more. So more confidence in communication, more power in computing, more insights in imaging and sensing. And our goal as company is to add quantum-based values to our customers and partners. And in the next minutes, I will give you a short preview of the things we do in the field of communication, especially for cybersecurity applications. So I guess there is a long history of communication security, and secure or private communication is somehow established in the DNA of humans, because if you look back and look through history, you can find Caesar's cipher, for example, more than 2,000 years ago, where the Romans find a way to encrypt their messages. In 1976, a huge step was done by Whitfield Diffie and Martin Hellman with the proposal of the public key cryptography, which actually is the basis of our actual internet communication. But as you might know, with quantum technologies, there come some issues, if you want, or let's say some challenges. There are some publications you already have read about. If not, feel free. There is a link in my slide where you can find one article that the quantum computer gives us some threat about cybersecurity. And also the ETSI Institute just mentioned how secure our algorithms will be in the future if we have some kind of quantum computing power. And as you can see, especially for the RSA algorithms, there is a challenge at the end to secure our communication. But what will be the solutions? I guess you have heard in the previous talk a lot about post-quantum cryptography, one way to establish new technologies. And another approach, which I will talk about, is quantum key distribution, or short QKD, which is, from our perspective, a physical approach for security. So just let me explain how quantum key distribution works. So if you have a communication layer, let's say Alice wants to speak to Bob, then in QKD we establish a so-called quantum layer, a layer where we share information, or not information, where we share specific quantum states. And with the help of this quantum states, we can firstly make sure that the sharing of this information will be tap-proof, because it's a quantum state, and you will recognize if an eavesdropper wants to steal your photons, for example, you will recognize this in your information. And then this leads to symmetric keys. And these symmetric keys, Alice and Bob can use to decrypt and encrypt their messages and actually communicate via traditional layers, so the internet at the end. My talk is maybe a little special to the QKD systems you had heard in the past, because we, as Quantum Optics Jena, we built quantum key distribution systems with entangled photons. So what's an entangled photon? Entanglement is a very special state or a very special property of quantum technologies. It means we can entangle, for example, photons in their polarization. Means if we know the polarization of one photon, we actually measure it, we actually know the polarization state of the other photon, independent how far this is away. And you can imagine this is the property we need to establish at the end this symmetric key. So how does it work? We have a so-called EPS, entangled photon pair source. I will come to this later, which sends entangled photons, one to Alice, one to Bob. And they will stay entangled until you measure it. So if they arrive at Alice or Bob, and Alice and Bob measure them, then the entanglement, or the wave function collapse in a physical speaking way. And this will lead to the fact that we now have the state of this quantum state, or the definition of this quantum state, and then can use this to build up a key at the end. So at the heart of each entangled photon source, there is a nonlinear crystal, or more than one nonlinear crystals, where we pump laser light into and generate with nonlinear effect 2 photons, one will go to Alice and another one will go to Bob. To give you an example how such a device could look like, so that's one of our first products, our HoutDock device, which with a very compact design. So it's 10 times 8 centimeters. It will be plug-and-play compatible. And this will give you more than 1 million entangled pairs per second per milliwatt pump power, with a huge quantum state fidelity. And this will work at around 800 nanometer. It's more for the academia side designed. So after you receive or you send your entangled photons, there has to be some other steps to establish the key at the end. So you have to detect your photons, then you have to sift the data. Then we have some post-processing algorithms by means of error correction steps and privacy amplification steps. And then at the end, we will have a secret key, which is only known by Alice and Bob. And that's very important. Within the quantum layer, or within all your algorithms, you don't share the measurement, only the process or the measurement procedure at the end will be shared. And this makes quantum technologies, or especially QKD, so promising as new technology. So what we want to do as Quantum Optics Jena is building up customized photon sources, not only at 800 nanometer, we also have sources in the telecom wavelength range. For sure, you need to have some kind of analyzer systems, and then the steps going more into the information technologies, you have to have some kind of key generation system, key management systems, which is then able to plug into your established crypto boxes or the interfaces to make sure that you use the right keys for your transmission. But there are advantages, there are also disadvantages, and this is maybe some disadvantage of QKD at the moment. So the transmission of quantum states is limited also by physical laws. So we have losses Within fibers, for example, we have losses by transmitting light through air. We have losses if we connect systems. So in the future, we need some kind of infrastructure to build this up. And there are many consortiums and ideas on the way to build up QKD networks, which then will be used, for example, as trusted nodes, where you can put a new quantum key to your information and then share it further ways. Because at the moment, one distance lies in the range of, let's say, 50 kilometers to 120 kilometers, depending on your systems. So our vision as Quantum Optics Jena is to be a partner or a crucial system partner to building up quantum networks. If we are talking about quantum networks, we are speaking about satellite constellations. We are speaking about fiber networks, which we have to build up. And in some cases, we also need some kind of free space links to establish quantum key distribution networks. In the future, if we think about quantum computers, and we need to connect also the quantum computers from one location to another, there might be also the possibility, or there will be the possibility to use this entangled photons as source for the connection, because we have at the end flying qubits, which we use as information. So my last slide, I just want to mention, if you are interested in cybersecurity based on quantum technologies, feel free to look at the website of the Deutscher Industrieverbund für Quantensicherheit, DIVQSec. It's a consortium especially building up for QKD systems and cybersecurity. And also feel free to look, if you're familiar with quantum technology in general, the QBN network, where we also are a partner, to learn more about quantum technologies in general. So I thank you all for your attention. If you have questions, feel free to ask it now or speak to me in the speaker's corner after the presentation. Back to you, Roman.
Well, thank you very much, Kevin. That was really exciting to see the current state here of the research, and also what your company is building here is offering. I have a question myself, but let's start with the first question from the audience right away, because it addresses exactly this from your company. Did I understand it correctly, is the question, that your entangled photon source device is only available for research yet, so not for the industry?
No, so the example I showed is for academia. We also have entangled photon source at higher wavelengths, so 1300 or 1.5 micrometer wavelengths, which is then more useful for industry applications. But in this case, I only show the academia side due to IP issues.
Okay, that makes sense. Thanks for the clarification here. I'm interested in, you mentioned the limitations through losses. If I understood you correctly, then through fiber networks, the losses are so big that the distances are very limited that you can actually cover. I think you mentioned something like 50 to 120 kilometers. Are there approaches, are there ideas to extend this significantly? I mean, I understand that if you use satellite systems, you don't have the same limitations, but as soon as you want to stay earthbound and want to stay in fiber networks, then 50 to 100 kilometers is really not much, of course.
Yeah, so there is an answer. The answer will be using different kinds of fibers. So at the moment, we are talking about standard telecom fibers. They are a couple of years old as a concept. There are new concepts available where you have some kind of air modes, or you use air as a transition medium. You also will have losses there for sure, but you can specialize this for, let's say, longer transitions. Maybe in the future we will have quantum repeaters. So there is a lot of research going on as well in this case. So if we have quantum repeaters, we don't have to care about trusted nodes. So then it could be easily done to send information which are longer away. But at the moment, the implementation goes more in the direction of trusted nodes or using satellite constellations to provide the keys over longer distance.
Okay, thank you. So if you use repeaters, wouldn't the repeaters be a place to tap in potentially, or are they built in a way that it's inherently safe too?
Yeah, so it's very important to understand that's not a typical telecom repeater or where you can gain your signal or something else. So it's a quantum repeater. So where at the end, the quantum state, you should not measure the quantum states. So it should not be destroyed. It's only sending it further away without measuring it. It's a little bit strange. I think there are some years ahead of research to really get an industry product at the end. But we're really looking forward to work together with others to especially address this issue.
Thank you also for this answer. We have a number of further questions and we still have time, so let's go through them. One question is, do you use or recommend to use QRNGs, the chips from ID Quantique, for example, for random number generation?
Yeah, that's the nice thing about entanglement sources. So you don't need to have a QRNG. So that's another way to generate a QKD system. So it's another kind of protocol, if you want. In this case, it's often mentioned as prepare and measure. So you prepare your state at Alice or Bob's side, and then send the state to the other party. So that's not our approach. So our approach is really building up the system as based on physical laws. So we do not need a QRNG in our system to get it done.
Okay, exciting. One more question. Do you also have other devices of the system included, detectors, for example?
Yeah, so our approach is delivering complete QKD systems. We do not fabricate the analyzers, for example, for our own, but we have suppliers to really establish a complete QKD system off the shelf, if you want.
Nice, wow. Thank you so much. I think we're sending you off to the Meet the Speakers section. So if there's more questions, there seems to be quite a lot of interest here, which I really enjoy. And I wish you best of luck with the further development of your company and these devices.